Okay, we are going to talk about potential energy today, which is something that we haven't yet talked about. We've been dealing with forces. So Coulomb's law told us about forces on charged particles. And then we dealt with electric fields, which were like the force per unit charge, which was useful to understand the behavior that a charged particle would have if placed into some area around a charge distribution. So you know from your Physics 50 or your mechanics class that dealing with forces is really important to understand how objects move, but oftentimes it's not the easiest way to understand the motion of objects. Conservation of energy is a really powerful tool that can simplify a lot of the calculations when you're dealing with motions of charged particles, or motions of anything, but we're going to apply conservation of energy to charged particles. So we need to be able to define the potential energy associated with charges. And like we did with electric fields, we said electric fields were like the electric force per unit charge. We're going to introduce something called electric potential. No energy, just electric potential today. That is the potential energy per unit charge. So it will let us define the behavior of a prospective charge placed into a charge distribution without actually knowing what charge we place there. So that's where we're going. And as a question to get you thinking about this, I put on the board here. Consider two identical charges, so maybe two positive charges, placed near each other. What will happen if you release them? What do you think? Harpreet? What will happen when you release two identical charges placed near each other? They're going to repel, so they're going to move apart. Okay, so because they're moving apart, that means they have some kinetic energy. So if we release them, they move apart, they gain some kinetic energy. Where did that energy come from? Yeah, so there's electrical potential energy. It must take work to bring them together, and that work goes into potential energy. And then when we release them, we can get it back as kinetic energy. So that's the idea of what we want to do. And we'll start by talking about electric potential energy. Okay, so we've considered what happens when we release these charges. They acquire some kinetic energy. That kinetic energy comes from stored electrical potential energy. Where was it stored? If we have a spring and we compress the spring, we increase its potential energy. We can say that energy is stored in the spring. Where is the energy stored if I take two positive charges and I bring them together, increasing the potential energy?
Electric field.
It's in the electric field. Yep. So energy gets stored in the electric field. Okay. Now, electrical forces are conservative, meaning if we bring two charges together, we do work. That energy gets stored. When we release them, we get that energy back. And so we have for the work done in an object, if you think back to Physics 50 or your mechanics class, the work done is force dotted with displacement. And if the force is not a constant, as your object is moving along some line, we can calculate the work done by integrating the force at any given position dotted with the path that the object takes. And of course, if the force is constant, like if you have gravitational force mg, and you lift an object up to a height h, if the force is constant, this integral just becomes the force times the displacement, mgh. But in the case of electric charges, it's probably not a surprise that the force is going to be changing. As the charges move further and further apart, the force between them is weaker and weaker. So if we take two charges and we bring them together, the force that we have to push with to bring them together gets stronger as they get closer and closer. Okay, so we're going to have to make use of this integral definition of work. And the reason that's useful is work can also be written as a change in potential energy. The work done by a conservative force is minus the change in potential energy. So if we do work to take two charges and bring them together, the work we do goes into the potential energy, of the electric field into the electric potential energy. And if we're doing work bringing the charges together, the electrical force is doing negative work. So that's why we have this negative sign here to denote the work done by a force is minus its change in potential energy. So we can use this. If we can take this definition here and write out the force between two charges using Coulomb's law, which we know how to do, and then take our two charges and move them close together, we can calculate how much work is done. And once we know that, we can figure out what the change in potential energy must be. And from that, we can come up with an expression for the potential energy of a charge in the presence of another charge. Okay. So before we do that, I want you to think about the various parameters that we're going to need to do this calculation and try to determine at least their sign, whether they're positive, negative, or zero. So here's the situation. We've got a pair of charges. One is fixed in place up here. And for the purpose of this example, it's going to be a negative charge, minus capital Q. And then our other charge is over here initially. It's also negative, and we'll call that minus little q. And we're going to take it from far away, and we're going to move it closer and closer and closer to the other like charge. Okay, so we're going to do that by applying a force to it. So here are the 5 different quantities that you need to categorize. The work done by the electric field. Let me just leave it at that. The work done by the electric field. The change in potential energy of the system. The net work on minus Q. What do we mean by net work as opposed to just work? What's the difference? Agree? It's the total work, yeah. So if there's more than one force. In this case, there's an electrical force acting on this charge. Is it attractive or repulsive? It's repulsive. So it's not going to move in on its own. An external force has to push it. So there's 2 different forces acting on it. An electrical force repelling and some, external force pushing it in. So the net work would be like the total of those 2 forces, the work done by those 2 forces. The work done by the external force is only the pushing force. And the potential difference, we haven't discussed this yet. So maybe this activity is coming a little early. But let's just call this the potential energy difference between the final and the initial point. So see if you can work with your groups to categorize these 5 quantities as either being negative, 0, or positive.
They're repelling each other?
So the charges are the same and they're repelling each other. So there is a force on this little charge here pushing it to the right.
I didn't see there was one on that one and not the other one.
Okay, so there's a force pushing it to the right, an electric force, but the charge is moving to the left. So what does that mean in terms of the work done by that force? It'd be negative, yeah. Okay, so this first one is negative. How about the change in potential energy? Yeah, is it Jared?
Yeah, it would be positive.
Okay, why do you say positive?
As you bring it closer, the potential energy should increase.
Okay, because it's taking work to bring it closer. You can also the work done by the electric field is always opposite the change in potential energy. So if one was negative, the other one was going to be positive. It's hard to push them together, just like it's hard to lift something up, because we're increasing the potential energy. How about the net work on minus Q, this charge up here? The net work, or the total work. Eli?
Would it be 0?
It would be 0. Why do you say 0?
Because the work done by capital Q will balance out with the work done on lowercase q.
Yeah. Okay, so if we're pushing it at constant speed, we're applying a force to the left that's equal and opposite the electric force pointing to the right. Otherwise, there'd be an acceleration. And so one does positive work, one does the exact same amount of negative work, so the total work is 0. Okay, so what about the work done by external forces? This is us pushing it to the left. What's the sign of that? Vincent?
Would it be positive because it's pointing in the same direction as like the movement?
Yes, it would be positive because it's pushing in the same direction as the motion. So we should get this, and the potential difference, and my apologies, we haven't introduced potential difference, but it's like the potential energy difference. That's going to be positive as well because the potential energy is increasing. Okay, so when we talk about potential energy in physics, it's really only ever the change in potential energy that matters in terms of understanding the motion and the behavior of objects. So back in mechanics, when we had something like a cannonball being shot and falling down, if we wanted to talk about its potential energy, there's some potential energy here at the bottom and some potential energy at the top, but we typically would define the height at the bottom as 0. And if we do that, then we can say there's some initial potential energy, and at the end of the trajectory down here, there's no more potential energy. It's completely arbitrary. We could have defined potential energy to be down here, somewhere down here at sea level to be 0, and then there'd be some amount here and more here. But if we choose sort of the final state, if we take and allow an object to move to its point of lowest potential energy, we call that final state 0 potential energy. That's something that often makes problems easier and makes sense to do. And we're going to do the same thing for electric potential energy. So let's take two charges. Let's say these are two positive charges. Imagine them close together, and we release them. Where do they go? Far apart. Yeah, so they split. They end up far apart. How far? It's basically infinitely far apart. Right? There will always be some repulsive force that gets weaker and weaker, but assuming that they're able to move, they will continue to move further and further apart. So we're going to use the charges infinitely far apart as our 0 potential energy state. And that kind of makes sense because if they're far enough apart, then we can say they're no longer interacting with each other. Right? The force between them is negligible. So if we call that 0 potential energy, when we bring them together, the potential energy will go up, and we'll always have some positive potential energy when we bring them together. All right, so let's go back to this problem that we discussed the sign of the various quantities. And now let's try to work out the specific values. So here's my little charge. And for this case, I'm going to consider two positive charges rather than two negative charges. Does that change anything in terms of the signs of any of the quantities we calculated? No, because it's still repulsive. Okay, so it doesn't matter. So initially, my positive test charge over here is at infinity. And I will move it to the left. And so I have to apply a force. This F sub A is the applied force pointing to the left. That's me pushing on it. The electrical force is pointing to the right, and it has a magnitude given by Coulomb's law. And so at some point, when I'm moving it in, it's maybe right here. And eventually, I will push it all the way in to a distance r away from the other charge. Okay, so to calculate the potential energy of this situation, two charges near each other, a distance r apart, I'm going to calculate the work done as I move the object from infinity to r. I've written it the other way around. I've actually written it as from r to infinity, but I want to calculate the work that I do bringing it in from infinity to r. And so that's the applied force dotted with the displacement. And that amount of work goes into the potential energy. Okay, so the applied force I have from Coulomb's law, right? I had it up here. It's my kqqq over r squared. In this case, r is going to be this variable x. And that applied force is pointing to the left, so I have a negative sign and an x hat. Right? X hat just means to the right, and so negative x hat is to the left. So I'm going to dot that with my little element of displacement dx and integrate all the way from x equals infinity all the way down to r. Okay, so all this stuff, q1, q2 over 4 pi epsilon naught, and the minus sign, those all come out of the integral. Those are constants. And what I'm left with is the integral of dx over x squared. So that's going to be minus 1 over x. So here's our minus 1 over x. You can just check this. If you take the derivative of minus 1 over x, we would bring the minus sign. We'd write this as minus x to the minus 1. The minus 1 would come out and cancel this minus 1. And then we'd reduce the minus 1 to a minus 2, which gives us the x squared in the denominator. Okay, so this is the integral. And we have to evaluate it from r to infinity. And I mentioned that I wrote these limits backwards. It should be from infinity to r. So at r, I get these two minus signs canceling out, q1, q2 over 4 pi epsilon naught r. And at infinity, I get 0, because it goes into the denominator. So the end result is the work here, and this is calculated, this is written correctly, even though my work has an error in this, the order of those definite integral limits. Okay, so this is the work that's done. We can check this. If q1 and q2 are both the same sign, if they're both positive or they're both negative, then it takes positive work to bring them together. And the closer I bring them together, the smaller this value of r, the more work it takes. So that makes sense. If q1 and q2 are opposite signs, so I have like a positive charge and a negative charge, they're going to get pulled together. So I actually have to do negative work. I would have to like hold them apart to prevent them from smashing into each other. And that's what I see here. If q1 and q2 are opposite signs, I get negative work. Okay, so the work that I do bringing them together is the change in potential energy. So we can write the potential energy this way, just the same expression that we got for the work. And notice that in the case where the charges go infinitely far apart, r is infinite, and the potential energy is 0, which is what I wanted. I wanted the 0 point of potential energy to be where they end up if I just release these charges and let them go. Okay, so this expression for potential energy looks very familiar, even though it's different than the equation that looks similar that we learned for Coulomb's law. Right, this was Coulomb's law from chapter 5. This is the potential energy expression from chapter 7. They both have a 1 over 4 pi epsilon naught. They both have a q1 times q2. And they both have this r in the denominator, but one is r squared. Okay, so it's really easy to mix these up, right? You'll do work with this expression. You've done work with this one. You're on a quiz. You might try to write the expression and write the wrong one. How can you keep these straight? Any thoughts or ideas on how you can, other than just sort of brute force memorization? Yep.
That one's force, the other one's work done. The work done basically force times distance, and distance basically r, so it cancels out one of the r's in the bottom.
Yeah, exactly. So energy is like work, which is a force times the distance. And if we look at these two expressions, this expression for force has an r squared in the denominator, so we have to multiply it by a distance to get something with the dimensions of energy. Okay, so you can use that, the dimensions, and any equations you remember that relate energy to force, work to force, to help keep those straight. Okay, so we can have potential energy between 2 point charges, but we can also have potential energy from a whole collection of point charges. So imagine we've got some test charge Q naught here, and charge Q1, Q2, and Q3 at distances R1, R2, and R3. Then we can talk about the potential energy associated with this test charge Q naught. And can you guess how we're going to figure that out? Or maybe you can read the bottom of the slide. But if we have 3 charges around it instead of 1, we're just going to add up the potential energy for this pair of charges, plus the potential energy for this pair of charges, plus the potential energy for this pair of charges, to get the potential energy of this charge, Q naught, in this distribution of 3 charges. Okay, so we can write that in a general form like this. This is just the same expression we had for potential energy between 2 point charges. But now instead of calculating it just for one of the surrounding charges, we're going to add up all of the surrounding charges and their distances in this calculation. Okay, so that's potential energy. In electricity and magnetism, we don't really work directly with potential energy very often, but we work a whole lot with something called electric potential, which is very closely related. So I want to go back to something that's more familiar, which is gravity, and talk about the relationships between gravitational potential energy and electrical potential energy. And this will help us motivate what this electric potential is. So gravitational potential energy is created when work is done against a gravitational field. Right? G points downwards. The acceleration due to gravity points downwards. If we lift an object up, we're doing work and creating gravitational potential energy because we're pushing an object against that gravitational field. So think about what the electrical equivalent of that statement would be. Electrical potential energy is created when work is done against an electrical field. We're just replacing the words gravitational with electrical. Gravitational potential energy is often treated as 0 for a mass at a height of 0. If I have something on the floor, I could say that has 0 potential energy. Or if we're dealing with celestial objects like the moon and the sun, we say there's 0 potential energy if they're infinitely far apart. Electrical potential energy is treated 0 when the charges are infinitely far apart. So that's similar to the universal gravitational law that we had like for celestial objects. Gravitational potential energy depends on the mass of the object I'm considering. If I have a brick and I lift it up, I'm storing some potential energy. But it also depends on the mass distribution around it, which is the Earth. If I take that brick and I put it out into interstellar space, it doesn't really have any potential energy. I don't have to do any work to lift it or move it around. But near the Earth, I do. Okay, so we don't often think about that, but gravitational potential energy depends on the distribution of mass around my object. Electrical potential energy depends on the distribution of charge around my charged object. So if we want to know how much gravitational potential energy a mass will have, we have to consider all the mass around it. But typically what we do is we think about what effect all that mass would have, let's say the Earth. And we say, okay, it has the effect of pulling objects down with an acceleration of 9.8 meters per second squared. That'll be true for any object. And then once you have that, you can take your brick, or whatever it is, and you can say, I'm going to multiply the amount of mass in this brick times GH, which gives me the total potential energy. But that G, that number, comes from the amount of mass in the Earth and how far away we are from it and such. And it would be different on different planets. Okay, so we want to be able to do something similar with electric charge distributions. Figure out what effect some distribution of charge will have on a point charge, even if I don't have that point charge there, so that I can apply any amount of charge and just multiply it by this thing. And that thing is called the electric potential. Okay, so it's going to be equivalent to G times H. G times H is like, G comes from the Earth and how much mass there is, and H is how high we lift something. And different heights, the top of the table, the top of the sixth step, the bottom step, all different heights. If we know those heights and we know G, then we can put any mass on the top step, on the bottom step, on the top of the table, and immediately calculate its potential energy. And we want to be able to do the same thing with electrical potential energy. Okay, so that expression that we had for the electrical potential energy from a distribution of charges right here is our starting point. And we want to say, what is that electrical potential energy per unit charge that I place here? So Q naught is my little test charge that I'm bringing in from infinity to this charge distribution. So I want to be able to write an expression that's useful for calculating the electric potential energy for any amount of charge. So let me just divide out the Q naught here. And when I do that, I get what's called the electric potential. We use the letter V to represent that. In circuits, this is known as the voltage. It's probably a familiar term. Voltage is electric potential energy per unit charge. And we're going to introduce it in free space with electrostatics. We're going to apply it when we get to circuits next week. Okay, so it has the same form. We just divide the electric potential energy by Q naught. Okay, so another way of saying that is the electric potential, or the voltage, is the potential energy divided by the charge that I'm considering as part of my, as a charge that I bring in that takes work to move into my charge distribution. Alternatively, we can say the potential energy is the charge at a point times the electric potential at that point, or the voltage at that point. Okay, so based on just these relationships, what can we say about the units for V? Yes?
Joules per coulomb.
It's got to be joules per coulomb, because potential energy has SI units of joules, and charge has SI units of coulombs. So the electric potential must have units of joules per coulomb. But we give it a secondary unit called a volt. So a 9-volt battery provides 9 joules of energy for every coulomb that moves across its terminals. That's what that means. Okay, so a volt is a joule per coulomb. And for a single point charge, we can write the electric potential around that charge as Q over 4 pi epsilon naught R. That just comes from our expression that we had derived for U. The potential energy between 2-point charges was 1 over 4 pi epsilon naught Q1, Q2 over R. And I'm just dividing out one of the charges to say this is the potential due to a single charge. When I bring another charge near it, I have to multiply that other charge by this potential to get the potential energy. Okay, so this expression here is going to be useful because if we can find the potential from a single point, then we can just add up the potential from lots of different points to get the electric potential from a charge distribution, which is something we're going to want to do. Okay, so if our charge is spread out over some object, we are going to integrate, which is just adding up all the charge. Okay, so let's start with something that's, I already mentioned this, but let's start with a simple calculation, which is find out how much work is done by a battery when 1 coulomb flows from the positive terminal to the negative terminal. So this is a 9-volt battery here. The work done by the battery is the change in potential, it's minus the change in potential energy. So when a coulomb goes from the positive terminal to the negative terminal, it's going down in voltage by 9 volts. Okay, so I can say that the work done is minus the change in potential energy, and the potential energy is Q times V. So this is minus Q times delta V. And if I go from the positive terminal to the negative terminal, I'm going down by 9 volts. So I have 1 coulomb and a change of minus 9 volts. That's 9 coulomb volts. Or 9 coulombs, and a volt is a joule per coulomb. So 9 joules of work is done by the battery, pushing a coulomb from the positive terminal to the negative terminal. That energy comes from chemical energy stored in the battery. Sorry, that was me knocking the power supply off the plug. Okay, so that's great, but a coulomb is a lot of charge. What about just a single electron? A single electron would flow, when we connect this battery to a circuit, we can think about positive charges flowing from the positive terminal to the negative terminal, because that reduces their potential energy. Which way would an electron flow, since it's got negative charge? Well,
Negative terminal?
it would flow from the negative terminal to the positive terminal in the opposite direction, since it has the opposite charge. So if we wanted to figure out how much work was done in that process, we would have, here we go, our negative charge. And remember, an electron has like 1.6 times 10 to the minus 19 coulombs worth of charge and is negative. And the voltage is going up by 9 volts from the negative to the positive terminal. And the work done is minus the change in potential energy, so that's why I've got this minus sign here. And so that gives me a positive 14.4 times 10 to the minus 19 joules. So when you're dealing with like individual electrons, energy units of joules are really inconvenient because they're way too big to talk about the energy of individual electrons. Therefore, we use a different unit, the electron volt. So one electron moving across 9 volts has a change in potential energy of 9 electron volts. And if a volt is an energy per unit charge, and an electron has one elemental unit of charge, then an electron volt is a unit of energy. And it's a much, much smaller unit of energy, and it turns out to be more applicable for individual atomic particles. So you sometimes see like electron volts used as a unit. Okay. Sorry, my slides skipped ahead a little bit. I don't think I'm quite ready for this one. There we go. So, in theory, if we're given a distribution of charge, we have a sphere or cylinder or something like that, and it's got charge spread over it, like the types of problems we've been doing, we can calculate the electric field from that distribution. And we start with something that looks like this. Right? This was basically the electric field from a single point of charge, dq, and the integral is adding up all the points of charge that we have. So we can do the similar thing for the electric potential. We can find the electric potential from a distribution of charges by finding the electric potential from a point on that distribution that has a charge of dq. And then with this integral, we're adding up all the different points. And generally, this is a little bit easier to evaluate than this integral. Because while this integral is for an electric field, which is a vector, and so we might need to consider the x and y components separately, Electric potential is a scalar. So we don't have to consider direction or make arguments about some of the components canceling out or taking the cosine of angles to get components or anything like that. But we can also go in the other direction. If we're given the field, we can figure out what the potential is. So instead of starting with the charge distribution and figuring out the field and the potential, if we know the field, we can go directly from this to this. And the way that's going to work is we can use the fact that work on an object going from A to B is just force dotted with displacement integrated along the path from A to B. And the electric force is the charge of our object that's being moved times the electric field. Okay, well that's the work done, which is minus the change in potential energy. And if we divide this by Q naught, then it becomes minus the change in potential. Potential is potential energy per unit charge. So let's take the work done per unit charge, and that's going to be minus the potential. So the potential difference between points B and A, so my particle started at point A, I moved it to point B, and the change in potential between those 2 points is just going to be minus the integral of the electric field integrated along a path from A to B. Okay, it's just what I get left over from this integral when I divide out the Q. So if I know the electric field, in theory, I should be able to determine the change in potential between any 2 points if I know the field between those 2 points using what's called this line integral. I'm integrating the electric field along a line that connects points A to point B. And this minus sign tells me that if I'm going along a field line, then the potential goes down. So I've got a positive charge here. Its field points radially outwards. Another charge, positive charge, if it moves along that field line, its potential energy goes down. So if I'm moving along a field line, the electric potential must go down. Okay, and then the opposite is true. In the opposite direction as a field line, the potential goes up. So I'd like you to work with your groups to try to categorize these 9 different scenarios, which I'll describe in a little bit of detail here in a second, as having a change in potential energy that's either negative, 0, or positive. Okay, so for situations 1 and 3 here, we've got electric fields lines that point to the left, and we've got a path. We can imagine moving a particle from the right side to the left side, or from the top to the bottom. That's what this arrow represents. If you move a particle along that arrow, does its electrical potential energy, or in other words, is the electric potential from the top to the bottom, is that change negative, 0, or positive? Right, so change is always the final minus the initial. For points, or for 2, 4, and 6, we've got the same sort of geometry set up, and we're moving along a circular path between B and D, or here we're moving from A out radially to B, along a circular path, and then into C. And yeah, I think the rest are self-explanatory. If you just imagine moving a charged particle along that arrow, trying to figure out if the electric potential that it sees goes up, down, or stays the same. Okay, so see if you can sort these numbers into negative, 0, or positive. Okay, so let's check in. What do you think for number 1? Anyone shout out negative, 0, positive? You just shout it out. Negative. Yeah, 1 is negative. How about 2? 2 is 0. 3? 3 is 0. 4? I heard 0 and negative. Let's check this out. When we go from A to B, we're going along a field line, which means the potential is going down. When we go from B to D, we're not changing the distance from our charge, so the potential energy is not going up or down, which is why 2 is 0. And then from D to C, we're going against a field line. So the potential is going up. By the exact same amount, it went down from A to B, assuming that A and C are equidistant from our center. So that tells me that 4 must be 0. Bella?
Can you explain how the field line is?
Okay, so the two that show the field lines, if we're moving along a field line, the potential goes down. If we're moving against a field line, the potential will go up. And if we're moving perpendicular to the field lines, then our potential is not changing. And so here, how you can think about this is, what if we went directly from A to C around a curve? Then this one would look just like number 2, just drawn a little bit smaller. Right? And so it actually doesn't matter what path we take, whether we go directly from A to C or whether we pass through B to D and back. So this one has 0 change in potential energy. Okay, given that, what do we know about 5? It's 0 as well, because I said it doesn't matter what path we take between A and C. They're the same distance away from Q. So our 1 over 4 pi epsilon naught Q over R, we have the same R at point A and at point C. How about 6? That is negative. We are going to a lower potential as we move further away from our charge. So here's our expression for the electric potential. Because it's got this 1 over R, when we get further away, the potential goes down. And that's what we've got going from A to B. And then no change in potential from B to D. Okay, so 7. Positive. Okay, so that's a little confusing because we just said going from A to B, the potential went down, and here you're saying positive, yet you're right.
The charge of the electron is different.
Ah, right, this is a negative charge now. Okay, so our field lines here are coming inwards. So since we've got a negative charge, now it's moving away from it is actually going against the field lines and increasing the potential. Okay, 8. 8 is negative, yes. And 9 is 0 for the same reason that 5 was. We're not getting any closer or further away from our negative charge. Okay, let's actually stop here, and we'll move on to the quiz. So you won't need anything other than a pen or pencil.